Demand paging, the next topic. So bring a page into memory only when it is needed. So if a page needed, you can replace the page. Otherwise, no need to replace the page. So for this, you need less IO and memory is less, faster response, and more users can use that page. Page is needed, reference to it. So whenever a page is needed, you have to choose any one of this. If it is an invalid reference, about to search the page, about searching the page. And if it is not in memory, bring that page from any other backing store into the memory. This is what you are going to do whenever a page is needed. And this is a diagrammatic representation of transfer of a page memory to contiguous disk space. So you can see that in main memory, you have program A and program B. And you can see some of the page blocks from 0 to 23, which is available. See, suppose seventh page is which is available in the main memory is not needed now, and the 17, 18, 19th page is needed. 4, 5, 6, 7 pages not needed. It can be swapped out into the from the memory to the backing store. And whichever page needed is 17, 18, 19 now. So those pages can be swapped in into the main memory from the backing store. You have in the page table, you have valid or invalid bit 1, which means the page is in memory, and 0, which means the page is not in memory. Initially, it is set to 0, and whenever the page is available, then the bit will be converted from 0 to 1. So this is the page table snapshot, which tells you the valid and invalid bit. Page table when some pages are not in main memory. So logical memory you have and the physical memory with the page table and the backing store device. So you can see that valid and invalid bit. So in which 4, 6, 9. So that means 0th page, 2nd page, and the 5th data. It's not a page, it's actually a data here. So therefore, a data is available. 4th data, that is 0th data, 0th page data in the 4th frame because it has the valid bit. And 2nd page data, that is C. 0th page is A. So A, C is valid because it is available in the physical memory, and similarly 5 is F, so it is available in the ninth position of that is ninth frame frame number in physical address. So it is been given as a valid bit. So you can see that ACF is in physical memory. So some of the pages, that is B, D, E, when you see it is available in the backing store. So the logical memory contains only ACF, which is available in physical memory. Other things, B to H is certain things, certain pages are not available in the physical memory, which is available in the backing store. We can see this in this diagram. And what is the page fault? If there is ever a reference to a page, first reference will trap to OS, that is page fault. OS looks at another table to decide whether it needs to avoid the invalid reference. It needs to avoid the reference, that is the page table, and or it will check whether it is not in memory. You have to get it from the backing store. So if that particular page is not available both in memory and backing store, it is not possible for the user to reference the page. So you need to abort the searching process. And if it is not, then if it is in memory, you have to swap it, means from the backing store, you have to follow these steps. Get the empty frame, swap page into frame, reset the tables, and valid bit to from 0 to 1. Restart the instruction, and recently used block needs to be moved as a victim. This is what we have seen in the page fault algorithms. So steps in handling a page fault. So the first step is the load M is the command, that is the reference. You go to the page table and find the frame address, that is I, and you can see that the next step is a trap. If that particular I, which means invalid bit, that means that particular load M page is not available in the page table. The corresponding frame address is not there. So that's why it is given as invalid page. So therefore, we don't need to search it in the uh, physical memory. It is not available. So therefore, it's a trap. So you go into the operating system and say that error, that is the addressing error. This particular page is not available. So suppose in the third step, if it is available in the backing store, then you can go for the fourth step, that is bring in the missing page. So you have to find the free frame in the physical memory, and you have to bring in the missing page from the backing store into your physical memory. And once you bring in the into the physical memory, you can set the frame address, that is physical memory address, into the page table. So you have to reset the page table and change the validation bit into V instead of I, because now we have at the first time the user searched in the memories, the memory, the CPU searches in the memory, physical memory, it is not available. So it and also the bit which is given in the page table is I, which is invalid, it is not available. So therefore, it shows the error. But as it finds it is available in the backing store, you have to bring in the missing page after finding the free frame in the physical memory and note down the address frame number and store it in the page table. So you have to reset the page table. So now it is available in the physical memory. So therefore, the invalid bit needs to be converted into a valid bit. So that is the fifth step. So after doing the fifth step, again you restart the instruction, that is load M. So what happens now? It is available in the page table. So the bit will be V now, and it finds the frame address, and again it goes for the frame address, and the frame address, the command will be executed. What is the command? Is load M. So the M is loaded into the physical memory. So the command will be executed. So this is how the page fault needs to be handled. What happens if there is no free frame? So you will go for the page replacement algorithm. So no free frame is available in the physical memory. So you have to swap in and swap out the pages which is not used according to any one of the algorithms what we have seen, either LRU or FIFO. You can or optimal page replacement algorithm. You can swap in and swap out the pages and take a victim page and replace that page. So you have to use the algorithm and the performance. You need an algorithm which will result in minimum number of page faults. So we have to choose the algorithm according to the minimum number of page faults. So the performance should be good with a minimum number of page faults. So choose a particular algorithm for the string, because for every reference string, the algorithm works in a different way. So therefore, you have to choose any one of the algorithm in order to make the page fault getting decreased. That is our main motto. So same page may be brought into memory several times. That is a victim page. So you have to avoid that victim page. So using that clock replacement algorithm, second chance algorithms, counting algorithms, you can use that. Same page. You can avoid that same page being hit for as a victim for changing the other page from backend store, that is for the page replacement. So if a process does not have enough pages, the page fault rate is very high. So this leads to low CPU utilization. So when the page fault happens, it will give you a low CPU utilization, and the operating system thinks that it needs to increase the degree of multi-programming. What is degree of multi-programming is so more than one program needs to be executed at the same time as the degree of multi-programming. So if the CPU or if the operating system is working on 6 programs at the same time, and it finds happens many page fault, that is pages not available in the physical memory. So many page fault happens, which means that it will think it needs to increase the degree of multi-programming. So instead of using 6 programs at the same time, it has to use 8 programs at the same time, so that number of page faults get decrease when you go for a number of frames, that is number of programs, that will be again divided into a number of pages, and when number of pages increases, number of frames also increases. When number of frames increases, page fault gets decreased. So that is the way the operating system thinks in order to increase the degree of multi-programming. So thrashing is a process is busy swapping pages in and out. So that is called as thrashing. So the thrashing should not happen um, more. So you need to avoid it. So because in order to avoid it, the OS will do the degree of increase the degree of multi-programming. So which makes the once you increase the degree of multi-programming, the CPU utilization will be more. So that the time when the CPU is not used effectively, that time is called as a thrashing time. So more number of pages needs to be swapped in, swapped out, which means physical memory is not enough to hold the more number of pages. So that is shown in this diagram. So the time when degree of multi-program is decreased, thrashing happens.